So welcome back. And now we're picking up where we had left off last week. We talked about the monopoly pricing. The monopoly pricing doesn't mean that the supplier never has any constraint on their pricing. I mean, the demand curve is still the constraint, right? Because as the prices increase, the demand does go down. So you're just constrained by the elasticity of the demand itself and not constrained by any of the other suppliers. That's what the monopoly pricing means. Okay? Now, and we figured out how you maximize profit and how do you maximize revenue. And then we'll talk about this idea of the maximization of the net social benefit. So that's our next sort of the idea that we're going to discuss. We did talk about this, but let's talk about the last thing, which is the maximization of the net social benefit. Okay. In terms of the benefit for the consumer, the benefit is the utility or the willingness of the pay that, that people will be willing to pay for something. And how much people are willing to pay, that is a good measure of how much utility they are deriving from paying for that service or product. Okay. Obviously, different people will have different utilities and so forth. And different will have different demand curves. But the net benefit, overall, the net benefit is benefit minus the cost. And if you want to define, if you want to maximize the net benefit, you're going to do benefit with respect to the quantity produced minus the cost with respect to the quantity produced. Then you take the derivative of both and set that equal to 0. Okay. And when you do that, essentially what you get is this equation, which is marginal benefit MB, which is benefit, the derivative of benefit with respect to Q, and then equal to marginal cost, dC over dQ, which is the cost of producing one additional unit. Right? And this is the demand curve expresses the marginal benefit of an additional unit of consumption. So if you look at the slope of the demand curve, that's your marginal benefit. But if you look at the slope of the cost curve, that gives you the marginal cost curve. So what you're looking for then is, if you go to the next slide, okay, the net benefit, net maximization of net social benefit happens when the demand curve meets the supply curve. And you must have heard of this, right? When supply and demand meet with each other, that's when you maximize the net social benefit. Okay. So now how do we figure this out? So this is, we already told that the marginal cost curve is our supply curve. And then this is what it looks like. And then the demand curve is downward sloping. Where they meet, that's the price and quantity demanded at which MB equal to MC, marginal benefit equals marginal cost. Now, here is the D. The gross benefit is A plus B, where A is defined as, A is the benefit captured by the supplier, because that's the money that they get from the consumer. And then the benefit captured by the consumers or the user is defined by A. So what happens, and then these P prime and Q prime are just simply the price and quantities that happen at that intersection of the supply and demand curves. So if you look at the cell or the point that I'm highlighting, what happens if the price rises? What happens to the benefit captured by the consumer? You can measure that by the area under the curve, under the demand curve, okay? It's the area under the demand curve. What happens if the P prime rises? What happens to the benefit captured by the consumer? Does it go up or down? What happens to the benefit captured by the consumer or area under the curve A, capital A? And you could see that this is what I'm highlighting here. So I'm going to just kind of sort of, so this is my area A. What happens to area A if this P prime goes up? If P prime increases, what happens to area A? Does it go up or down? Good. So yeah, I got some good responses here. You guys are exactly right. As P prime increases, as the equilibrium price goes up, the consumer share of benefit goes down and the supplier share of benefit goes up, right? That's the idea. And so that's why, you know, A and B are the areas that I'm interested in. And we call this A, the benefit captured by consumers and users, is called what we call the consumer surplus. Okay, we'll talk about this a little bit more when we talk about the benefit estimation. But for now, all you need to remember is that you're interested in the point where marginal benefit is equal to marginal cost. And that's where maximum net social benefit occurs. Okay, so let's go and do next slide. Let me clear out these annotations. So now we're adding one more layer. So remember, we talked about max profit pricing. We talked about max profit pricing. We talked about max revenue pricing. So I'm talking about a third element now, which is under the monopoly, how do you maximize the net social benefit? Okay, so I'm introducing a third concept, P triple prime, and P triple prime is basically this new point that I'm introducing, where the marginal cost curve, I want to draw it out here, where the marginal cost curve, this curve, meets the demand curve, this curve. Okay, so you can see that point is right here. This point I'm talking about, where marginal cost and demand curve meet, and you can extrapolate that point downward. Extrapolate that point downward to get Q triple asterisk. So this point is right here. Okay. And then if you project that point onto the y-axis, you get this point P triple prime, which is pointing here. And that's your maximum net social benefit price. Because we already talked about the max profit and max revenue prices last time, but this max revenue pricing or max net social benefit pricing is where marginal cost is equal to the demand curve. Okay, you guys all see the three different points, pricing points. One is for maximizing profit. One is with maximizing revenue. We talked about those in the last class. And today we just talked about maximizing of the net social benefit, where the supply and demand curve meet. Any questions about this? So we can see now how marginal cost curves are so important in terms of what the pricing ought to be, right? So cost is not about pricing directly, but they still play an important role in different pricing strategies. And this is sort of important to know. Now, when you do this, so that means that, you know, as a supplier, it's very important for me to be able to understand my cost structure. So that sort of is what I'm going to segue into now. I'm going to try to look at some of these cost modeling principles. So when you talk about cost modeling for two aspects of system performance, one would be cost efficiency, and the other would be cost effectiveness. Cost efficiency is about ability of the system to provide transport at a certain cost. It's cost per seat mile, cost per ton mile of available capacity. Cost effectiveness, they consider the actual transport provided at a certain cost. cost per passenger mile produced, cost per ton mile carried. And we are worried about efficiency, effectiveness, both. And remember, sometimes when we are talking carelessly as a layperson, we use these efficiency and effectiveness terms interchangeably. But in economics, those terms are not interchangeable at all. Efficiency and effectiveness are related concepts, but they are different, really. Okay? Efficiency is about what's the ability of your system that you're designing and how much it would cost. And effectiveness is actually how much service actually is it providing. Both aspects are more of interest. But as a policymaker, which one of these two interests you more? Efficiency or effectiveness? I'll take a minute to respond on chat. Which aspect interests you more? Efficiency or effectiveness? So it looks like the options that I heard from at least few of you guys was a little bit split in your responses. Actually, both aspects are of interest, but effectiveness is what we worry about more, because you think about the buses that run empty, right? Efficiency is about providing that bus service. How many seats can it carry? But if the bus is going to run empty, you don't want to provide more capacity than needed all the time, right? Maybe you want to provide some slack capacity, but you also want to look at effectiveness. How many resources are actually getting used before you put them out there? Okay, so we have to look at both efficiency and effectiveness. Any questions about this? Okay, so we are interested as a policymaker, policymaking folks are more interested in effectiveness and how effective the service is on the ground, how many people are using it, because efficiency is mostly about capacity of the system. Effectiveness is actually about how many people actually use that capacity that's available. So I hope you understand the difference between the two concepts and why effectiveness is more, useful for policymakers. There are two different techniques, two basic techniques to transportation cost modeling. And it's okay to rely on less accurate methods. One of these methods is more accurate. One of them is less accurate. One of them is more accurate. So there are two different techniques. One is what we call the statistical cost model, okay? And then engineering cost model. Statistical cost models are relationship between cost and decision and design variables based on previous cost experiences determined using some statistical methods. So maybe you look at, just to take your example that you're working on in your labs, that'll perk you up, I hope. So if you're working on your labs about the example of, let's say, what do you call, complete street conversion. And it's okay to rely on statistical cost model for what you're doing, because you're submitting a grant application at this point and you're figuring out, and so some semblance of statistical cost is okay at this point, because it's an accounting cost model. They're more aggregate models. So it's okay to look at historical projects that you've done or that your agency has done or that neighboring agencies might have done, where they did similar work. And then you look at how much did they cost overall, and then maybe you average out certain projects. Maybe you take 10 bike lane projects, okay, or 10 road diet projects and average out their cost per mile maybe, okay? And then you come up with a cost model that this is what it's going to cost me. In engineering cost models, they get way more detailed. And engineering cost models may be required for the contractor who's going to bid on that project. They might need to know precisely how much it's going to cost them so that they can give you a good bid for actually building that out. For planning purposes, statistical cost models are fine. You can do them down and dirty. You can do them quickly. So they're more like quick and dirty type calculations. For engineering cost models, you're looking at how much pavement you're going to pave, the exact details, the slopes, the cross slopes, everything so you need way more engineering details at that point when you get to the disaggregate cost model. Comprehensive cost modeling software, they're a combination of both of these techniques. But it's okay to rely on statistical cost models. Okay, because they're sort of quick ones to be able to estimate certain things. Some statistical cost model examples: road excavation cost as a function of width and minimum radius of curvature. So you look at different projects that had a certain width of roadway and then the minimum required radius of curvature, and you look at excavation cost. You look at multiple projects that were done in the past. You look at all their costs, and then you just look at these two parameters. Okay, W is the width of the roadway, R is the minimum radius curvature, and then you just fit a regression model using these two parameters and estimate alpha, beta, and delta using some statistical regression type model. And then you can do separate relationships that would be fit to data for different terrain types. You could do that too. And then use that model to come up with costs. Okay, and this is still a pretty sophisticated statistical cost model, by the way. And I don't anticipate that to be the case for your project, for your presentation, or for the raise grant that you're writing. No, I think we can even rely on some simple averages of past projects if you need to. Okay, so just roughly estimating the cost is fine for your purposes of the class assignment. And yours would be also a statistical model. But this is a simple but still somewhat sophisticated statistical cost model that looks at a lot of projects, maybe looks at different terrain types and estimate one model for different terrain types. Okay. Now, if you get to the disaggregate model and you still want to figure out the cost of excavation, you're not just going to look at minimum radius of curvature and width of the road. And you are actually going to look at end area, and you're going to cut sections of the road. Okay. And you're going to know how much does it cost per unit volume of excavation. And then you're going to use this complicated formula, which is essentially the area of the trapezoid multiplied by the length of the roadway segment. Okay. And you're cutting cross sections, and then using those cross sections to come up with volume that you're going to have to excavate. And then you're multiplying that by theta. So you can see how much more details this engineering cost model needs that is shown on this slide versus what I showed you on the last slide, which is a very simplified cost model. And that's what we call the statistical cost model or accounting cost model. But in here, I'll get much more accurate estimate of the cost. But this requires me to have a lot more details of the project. Okay? Questions about this? Any questions? Can I even pause for? Okay, so here are some differences. Engineering cost models are commonly used in cost estimation for facility location and design. But engineering cost models are too detailed for planning applications. Engineering cost models are usually more accurate, and they're adaptable to changing technology and condition for which historical data may not be too relevant. So if you're relying on some kind of a regression model of the past projects, and you now have a completely different technology, or the raw material has become much more expensive, then your statistical cost model may not be accurate anymore. Okay? So you might have to rely on engineering cost models, and that's something that you'll have to take care of. But also remember, engineering cost models are way more detailed, so you need a lot more information about the project. Okay. For transportation cost models, you'll need a bunch of information. You need comprehensive transportation system cost model should incorporate cost structure for 4 principal components of any transportation system: costs associated with the ways, costs associated with the terminals, costs associated with vehicles, and then the system-wide cost, which is safety, security, driver certification, network flow control, system management. And sometimes, you might not be able to rely only on engineering models or only on statistical model. You might have to, for ways, you might have to rely on statistical model, but then for safety, you might have to rely on more engineering models, for example, right? So you might have to do sub-models, different sub-models of cost for ways, for terminals, for vehicles, for system-wide cost. And each of those sub-models, some of those could be engineering cost models, very, very detailed, and some others might be statistical cost models, maybe not as detailed. And that's okay too. Okay, so you might have to use a combination of engineering and statistical cost models. Questions about this? Any questions? Now, when you're looking at these elements, different elements of cost, you have to figure out what is the most important component of your cost. Because see, for some modes of transport, some costs would be way more significant than others. And it's very important to get those correct in the right ballpark versus the minor cost. For example, if you look at the air transport and ocean shipping, the way costs are minor, right? You're talking just navigation aids. And in the scheme of things, those costs are very low compared to terminal and vehicle costs. Your vessels and your airplanes are much more expensive. Building ports and airports is much more expensive. So you have to make sure that you get your terminal and vehicle costs correct. For pipeline costs, the way and terminal costs are substantial, but vehicle costs are basically nothing. For highways, building the highways, although parking lots are expensive, but still compared to building of the roads and other facilities, terminal costs are relatively smaller. And then for railways, all components, the terminals, the ways, the vehicles, everything is substantial. So not one of those costs component dominates really in railways. So it's very important when you think about the transportation cost models, you think about what mode you're considering, and depending on that mode, certain submodels of cost would be more important and more critical than others. Okay. So let's think about these generic transportation corridor cost models. Vehicle unit costs and factor prices. So if you think about, this is sort of one way of figuring out the cost model. And I'll give you 1 minute to look at this, and then I'll talk about this. It'll be easier if you have seen this. So look at the cells, what they say, and then remember the key: the yellow cells are input, the green cells are final outputs, and the white cells are intermediate calculations. So let's take maybe 1 minute to look through this slide. And I'm going to pause recording in the meantime. Okay, so I hope you had a chance to look through this slide for at least a minute or so. And as you look through the slide, what do you see? You see all these things that you will require for a transportation corridor cost model. Okay, and then you'll use the vehicle power and performance characteristics, way and terminal design, and way and terminal cost. And then you'll use these to estimate with vehicle power and performance, you'll get the travel time and vehicle productivity estimates. And then you will, from way intermediate, you kind of, all these intermediate calculations would have to be done. You'll get your vehicle load, fleet size, traffic volumes, and then you'll get your vehicle cost estimates. And then vehicle cost estimates will be input of, or they'll be consisting of vehicle unit cost and factor prices, travel time and vehicle productivity estimates, vehicle load, fleet size, and how much fleets are you going to need, and traffic volumes and all that. Okay. And then you'll have to figure out how much stuff you need to transport, for example. So keep this in mind. One of the labs that we are going to work on this quarter will involve a sort of a practical application of this. Okay. So we are going to use our Excel, we'll use an Excel spreadsheet that will be about exactly this. That would be looking at different components of cost and sort of aggregating them together and finding out some ways of minimizing the cost. Any question about this slide? Anything that doesn't make sense? Any connection that are maybe potentially missing or anything? And by the way, this is just one way of representing. So you can think of this in the context of, let's say you're a company who's trying to open a port in an island, basically. Okay, and then they need to take the stuff from the port to where the people are or the warehouses are, and then port and warehouse and back. And they're deciding how many trucks are they going to need, what's going to be that cost of having that corridor from the port to the warehouse. Okay. We'll do a lab exactly on this a little bit later in the quarter. So here is like some major relationship. We talked about this. Fleet size and traffic volume depend on the demand, round trip travel time, and per vehicle load limits. Okay. Round trip travel time depends upon how good your road is designed. If the trucks can travel faster on it, how good are the vehicles themselves, vehicle weight and weigh condition and the maintenance standards. And this is exactly what we're going to work on. We're going to work on in our lab. We're going to work on what kind of maintenance standards should we adopt so that we minimize our cost, our total cost. And then once we figure that out, optimal total weigh cost and vehicle cost are a trade-off between facility and vehicle cost. So basically the idea is that if you design good roadways and good terminals, it'll cost you more, but it'll minimize the vehicle cost because your vehicles won't get damaged so easily. And same thing with the maintenance policy. If you keep the roadway up to date all the time, it'll cost you money, but it'll reduce the cost in terms of how much it takes to operate the vehicle or maintain the vehicles that you're running, right? And that's the trade-off. And that's the trade-off we are going to study in one of the labs that's coming up a little bit later, as I mentioned. Okay, specific submodels are typically used to represent those relationships. So what are some of the submodels? This first submodel is a vehicle cost model. Vehicle cost model is selection of suitable vehicle type and sizes to provide the transport that is required. Determine the size of fleet depending to meet the need. And when you determine the size of fleet, you just make sure that you have some buffer as well, so that if one bus breaks down or one of those tankers break down, then what happens? So you need some backup plans. And then determining the operating and associated cost per vehicle in the fleet. Okay. Vehicle costs and key components. A comprehensive vehicle cost model incorporates a variety of cost components. Cost of vehicle purchase, rental of fabrication, labor cost for drivers and other crew, fuel costs, tolls, parking, vehicle maintenance and repairs, storage when not in use, licensing, taxes, insurance, and permits and administration costs. All of these things are vehicle costs. Now remember, the key question is the one that I put asterisk on. These costs are variable. These are not fixed costs. But one that don't have the asterisk Those are your fixed costs. They're going to happen regardless of whether or not you move any cargo at all. Once you buy the vehicles, you're going to have those costs. Does that make sense? That the costs marked with asterisk are the variable costs. The other ones are non-variable costs, or sort of fixed costs. Okay? And they're fixed in the short term, tied to longer decision time. Questions? Okay. Now let's look at the fleet size. The fleet size and its composition, obviously if you have more demand, then you need more fleet size. If you can put more loads on one truck, then maybe you won't need as much fleet size. And if you can travel faster, then you won't need as much fleet size, right? So it's a simple sort of relationship, right? You could say, okay, if I can go faster, I can load up a lot, and I don't have as much demand, I'll need a very little fleet size. Okay. But on the other hand, if I have more demand and I can't load each truck more and I can't travel as fast, then I'm going to need a bigger fleet size. Now, but there are some questions involved. And these questions are, can transport needs at different places and times be met by same vehicle through repositioning or creative scheduling? So I don't have to buy as many vehicles. So that's one thing that could come into play. Is vehicle capacity weight limited or volume limited? This is important too, right? Because if it's weight limited, then the density of the stuff that you're trying to figure out becomes important. And sometimes it's volume limited. If it's about how much space you have to transport. Do peaking pattern negatively affect vehicle productivity and fleet size? You have to make your trips during congestion. Can you do some marketing so that people ship their stuff during off-peak period? So these peaking patterns can negatively affect vehicle productivity because they might be bogged down with congestion and so forth. So that's why you will see that a lot of truckers prefer to ride at nighttime rather than daytime because they don't want to encounter those peak hours. Customized vehicle types meet particular transport needs more efficiently. You might be better off ordering like 50 of the same type of vehicle or hundreds of the same type of vehicle because you might be gaining some fleet economies because, then you can, parts are easy to find if you're all your fleet is basically uniform type. Even though, they might not be so efficient in meeting individual demands, but they might have some economies of scale in terms of maintenance, in terms of, buying power that you will have if you buy more vehicles. And then last thing is how should current fleet size and composition reflect possible future changes in demand in vehicle technology? So that's another piece of information that we are going to need can I buy electric vehicle today? Electric trucks, for example. Would I have the charging capacity? How soon the charging capacity is going to come on board, right? So those questions have to be considered, technology questions. Okay. So when you think about fleet size and composition, how many trucks you need, and what kind of trucks should they be? A lot of sort of subtle issues that are involved, even though the relationship you might find is simple, like we talked about with demand, loads, and travel speeds, but these issues need to be considered. So here is sort of a simple calculation. So let's think about this. So I'm looking at here two different types of capacities. I'm looking at two different types of capacity. I'm looking at weight capacity. And I'm also looking at volume capacity. And you might need both, by the way. Okay. You can figure out the weight capacity using the formula Q times L divided by FUH. And all the terms are defined here. WC is the annual ton miles of needed capacity. So pay attention to this real quick. I'm going to go ahead and annotate this. Point lighting. So let's, oops. So let's look at this formula. WC is my weight capacity, annual ton miles of needed capacity, where Q is the annual transport demand in tons per year. Okay, tons per year. And then F will be equal to average load factor, fraction capacity used when loaded. Okay, F is the sort of a load factor, because you might not be able to fully use that capacity that is available with each truck. U is, capital U is average proportion of total annual travel distance operated loaded. Okay, so how much is the travel distance you're making? H is how much, L is the trip length in miles per load, adjusted for circuitry. So if the route is like, is not straight up, so you're looking at the total length of the trip. And H is the annual vehicle service hours per year. So what you do is you just multiply how much demand you need times the length, and you divide it by FU and H to get how much weight capacity you need. Once you figure out the weight capacity, you can determine what we call the volume capacity. It's just 1,000 times weight capacity divided by D. This 1,000 is there just to convert the weight comparison, but you multiply because you're trying to find the volume capacity that has a unit of feet cubed times miles, needed capacity, volume miles. And WC is measured in ton miles. Okay. Now, what you do is you figure out two different ratios. First ratio is R1. It's volume capacity divided by weight capacity divided by the volume capacity. WC divided by VC. Okay. And then you figure out R2, another ratio. And this another ratio is AWC divided by AVC, which is available weight capacity divided by available volume capacity. Okay. Now, if R1 is greater than R2, then what happens? If among these ratios, R1 is more than R2, then your number of vehicles will be determined based on the weight capacity. That means your weight capacity is the critical factor. But if R2 is greater than R1, okay, R2 becomes greater than R1, right? Then in that scenario, volume capacity becomes the critical one. It should be AC. Instead of ACW, it should be AWC and AVC, okay? This is, so weight capacity divided by available weight capacity. Okay. Times S. S is the overall running speed, and phi is the reserve fleet requirement. A 10% requirement would mean that you need 10% extra vehicles. Okay, 10% to be vehicles to be free at all times. Okay, and then you can use that formula to figure out what's the number of trucks that you're going to need. Okay, but it's important to remember why, if R1 is greater than R2, that means your WC or VC ratio is higher than your available weight capacity divided by available volume capacity. That means weight capacity is going to be your critical factor. Things change if R2 is greater than R1, then volume capacity becomes the limiting factor. So you have to go by, you have to determine your fleet size based on your volume capacity consideration. And then that, so this formula should be S times AVC times 1 minus 5. Okay. Questions about this? I'm going to pause here. Okay. Very well. Now, as you get to the point where you have to figure out your engineering cost models, then you have to think about the vehicle performance. So how does the vehicle performance work? It depends on the tractive effort, kilogram of force, and then velocity in kilometers per hour on the x-axis and y. So you'll see, like, when you're starting out from 0 speed and you're trying to pick up speed, it takes a lot of tractive effort to do that. But as speed increases, the tractive effort that's required goes down. And this shape basically reflects both transmission effects and the fact that the engine power is approximately constant. So this is sort of a chart that represents how much tractive effort you need at different speed level. Okay. So now let's think about how is that used to come up with what we call it's some kind of a cost model for tractive effort. Overlaying the tractive effort curve and the sum of air rolling and gravity resistance. So you could see air rolling and gravity resistance are charted here, the second curve is, and where these two curves meet, that's what we call the crawl speed. At that speed, the tractive effort is balanced out by all the resistance, okay? And then you can sort of move, the truck can move at, or the locomotive can move at that constant velocity, okay? We use the Davis equation to do that. I'm just giving you sort of, this is not necessarily transportation or transportation economics at this point. This is more into like mechanical engineering. It's good to have that, some knowledge of where these things are coming from, even though you might not necessarily have to use it, because most of the things that you're going to use, these things are going to be built in. Now let's talk about, when I'm thinking about engineering cost models, let's look at the fuel cost model. Okay. So energy consumed by the vehicle, once the vehicle speed profile along the highway or railway is determined, based on the simulation of vehicle performance and other factors, the fuel use can be calculated based on energy required to overcome the resistances in each homogeneous section. So let's see. E, the energy required will be maximum of RA plus RR plus RG. So it's basically the sum of those resistance times L, the length of the section. And so this is the energy that's required to overcome the tractive effort. And then energy needed to keep the engine going during idling and coasting and whatnot. And it's the max of that. And then you could say these are, again, these numbers might change. Fuel consumption rate, liters per kilogram kilometer of energy. You can figure that out by using these factors, 0.007, 0.021, 0.008. Okay, and then Q will be the amount of fuel consumed in the section. Is rho times E, where rho comes from these values. And then E comes from this equation right above that. And then you could have models, not just for the energy consumed, you could come up with amount of pollutants released or something like that. Okay. Again, it depends on how much is your resistance for a given section and how much energy you consume while idling and so forth. And again, engineering cost models may be necessary because the historical, cost models or they say statistical cost models may no longer be accurate because of the advances in engine technology. Okay, so that's why sometimes you do need these engineering cost models. But if you can rely on a statistical model, they won't look anything as detailed. For that, for the available cost, for the statistical cost models, you can simply have some chart from some historical data, and I picked it up from an old NCHRP project, really old. But you get the idea of a statistical cost model from that. Your automobile and truck fuel consumption at a given speed, gallons per 1,000 miles, and constant velocity, you can figure that out. For different grades, you will have different values of cost, and then you can figure out how much gallons of fuel are you going to use if you're able to drive at constant speed. So you can see at 35 to 40 miles per hour, you get the minimum amount of fuel consumption, okay, for trucks. And then this is the chart that sort of is relevant when we used to have that 55 miles per hour speed limit a long time ago. And these are the types of statistical cost model that was based off. Okay, so this is, you're simply relying on historical data rather than looking at the tractive effort on your segment of the locomotive and whatnot. Okay, so this is again a difference between two different types of model. You could look at, just like I looked at the fuel consumption, you could look at the oil consumption as well. Okay, so what I need to do is now, I'm going to go ahead and stop here because we've hit the 7:30 time.